Without any further ado, let's welcome Josh, and Josh, take it away.
Thank you very much. So I'm Josh from the University of Pennsylvania, where I work on software development for the Simons Observatory. I'm going to talk today about not the scientific Python stack. My whole experience over most of my career has been with the scientific Python stack, working on data visualization, data processing, all of that kind of stuff. But I'm here to convince you, the SciPy audience, that you too can build web services and make things happen. And why do we need a web service? Well, we're a telescope. This is a picture of our telescope. It's a radio telescope on the top of a mountain in Chile. It's in the Atacama Desert at 5,200 meters elevation. I think that's 17,000 feet. And we need to get the data from this observatory to North America where it can be analyzed. Now, as you may imagine, this looks like Mars because the Atacama Desert is used as an analog for Mars in many experiments, but it's in the middle of nowhere on purpose. And this makes moving data a little bit of a challenge. And we also produce quite a lot of data. So we produce, in terms of data that is packaged and ready to go to North America, about a petabyte a year. This needs to be moved to high-performance computing centers across the globe for analysis. So radio telescopes, I don't have time to go fully into radio astronomy, but they operate in a very weird way. You can think of them as having one pixel that scans across the sky. And so to make a picture of the sky, you need to use a year's worth of data simultaneously to make kind of one image. And that happens on HPC systems. And so part of this is that you need a lot of data just to make one image. And two, data is extremely precious. Like, if we lose a block of time, the noise there is all correlated and it causes lots and lots of problems. So we prefer to keep all of the data if we can. This is all kind of backed up by very different hardware landscapes between commercial enterprises and academia and kind of publicly funded projects like this. So as I kind of see it in the commercial landscape, it's very common to have much more control over the hardware and the software that hardware is running. So you can build a data lake or a data warehouse in S3, put all your stuff there, do co-located analysis, make everything happen. You control all of that. And if Amazon says, we're going to charge you $1 billion a year, you can say, well, no, I'm going to go to Azure or something, right? And you can build up your software stack with your hardware stack and make those kind of scale together. We don't have that kind of luxury. We do have access to some incredible compute, but we get it through time allocations. So we apply to various computing services, and they say, here is a block of computing time that you can use on our existing system. And that means that we have a kind of very constrained software and hardware environment to run in. All of our data needs to exist on parallel lustre file systems that are kind of talked to by Slurm schedulers and really kind of lower level analysis in terms of I run a Python script in a job scheduler and I get a plot out. And that means that our data has to exist on a POSIX file system, A/B/C/D.txt or whatever, right? We have to make our data appear in that kind of format. We do have one kind of benefit, though. So the NERSC National Facility has kind of somewhat recently had this kind of wonderful thing that they've created called Spin, which is just a Kubernetes cluster that runs Rancher, and you can run your persistent services there. So this is kind of a new thing to the academic landscape of like, oh, I can have a thing that runs all of the time. Now, I know in the commercial landscape this is a very common thing, but for us, this is relatively new. And the neat thing about Spin is that you can have access to those same high-performance file systems from your persistent services that you would use from the HPC nodes. So that gives us a little in here. So what does the data look like that we're trying to move around and like quite literally get down the mountain? Our data comes off the telescope, is ran through a series of pipelines, and is eventually reduced to books, which are folders filled with raw data files like this. Those books live in a standard POSIX file system with a fixed path for every book that was determined ahead of time that many, many people argued for many, many months about. And our core goal here is to make this file system appear on HPC systems elsewhere. You may think, oh, well, that's kind of just an easy thing to do. Just send it over the internet, sync it every now and then. There are two kind of major problems. One, we don't have enough storage space to store the entire history of the project. So we need to move some stuff off to slower storage. But there is another interesting quirk that is kind of a telescope problem. I would love to send all of this data with Globus. So Globus is a really great file transfer service produced by the University of Chicago for sending data across the network. This is an amazing piece of software, has a wonderful Python API, and allows you to send basically anything anywhere and make sure it goes over Internet 2 or the grid or whatever it is called in your local system. But this assumes that you have a nice internet connection. Right now at the telescope, we do have a nice internet connection, but that's a somewhat fragile prospect. This is what our internet looks like most of the time. Not a nice fiber that is 12 fibers all connected and we can get to the internet from anywhere. This little radio dish is how we get our internet some of the time. This is about a 50 megabit radio link, and that comes nowhere near enough to supplying enough bandwidth to get a petabyte of data down the mountain. So how do we get the bits off? Well, we use a much kind of older code, which is called Sneakernet. So on the right here, this is what we affectionately call the toaster. So someone comes along, they put a hard drive in, our data management system loads up the most recent data onto that hard drive, they get pinged, they remove it, and then they fly to North America with it and plug it in. And yes, this is genuinely the most easy way to get this data off the mountain and into North America. Problem, most data management software does not consider this a valid way to move data and does not support it at all. So we had to come up with our own solution. There are some wonderful tools that exist already for data management. A lot of them are rule-based. So these two kind of big players, iRods and Rusio, are amazing pieces of software, but they are rule-based. And so what that means is you say to the system kind of abstract concepts of like, I have 10 machines, I would like 7 copies of my data to exist at all times, and it makes it happen. The problem with that is that it assumes that there's a ton of network bandwidth available. If a system drops off and suddenly there are only 6 copies, it makes another copy somewhere, which it definitely should do. But we don't actually want to worry about the copies of our data that exist. We need to control the way that it flows. So that kind of necessitates a kind of more baseline solution. So this is what our service looks like. So someone, as I said, gets on a plane with some hard drives in a Peli case in Chile. They fly to North America, plug them in, and then we can Globus stuff the rest of the way. Each of our sites, so at NERSC, at Princeton, on the East Coast, in the UK, and in Chile, we have an instance of our server called the Librarian running. This Librarian basically makes sure that the data gets where it's going and that we didn't forget anything. Because as you can imagine, if you're carrying hard drives around, it's very easy to forget something, and you don't want to have to wait another week for the next hard drives to come. So what is the Librarian built with? This is where I would love to stand here and tell you all about the Librarian for 2 hours. You can read the proceedings if you want kind of more deep technical detail. My goal here is to tell you, like, here are the pieces that we assembled it with and why, and like hopefully you can use this information to not be as afraid of web services as scientists usually are. So at the core of the Librarian is a Python-based web server. So we built this on FastAPI and Pydantic. We chose FastAPI because of its tight integration with Pydantic. And what Pydantic is a data validation library that kind of effectively allows you to strongly type your Python objects. This is very useful if you're receiving data as JSON and you want to kind of automatically turn the strings into datetime objects or integers or whatever, and make sure that you get that data as it is supposed to be. There are a couple of other web frameworks that we considered. So there was actually an older code that we based this version of the Librarian on that was based on Flask. But we just saw Pydantic as such a big benefit that we do switch to FastAPI. So how does a FastAPI thing work? There's this kind of general belief of like, if I'm building a web service, it needs to be this like very polished thing. I don't necessarily agree with that. Not that the Librarian isn't a little polished, but FastAPI allows you to define routers. So these respond to specific kind of queries for a page. So if I go, in this case, to mywebsite.com/hello/world, and I send in the input model, which I've defined on the top there, I get back the output model. So all a router does is basically run Python code in response to receiving an object and produces an object. And that's a very simple way of explaining what these things do. And so we have routers that, for instance, say, here is a file I would like to upload. Do you have space for it, right? You send in the size of the file, and you receive a yes or no, this kind of thing. And then we want to add on some persistent metadata storage. So in the Librarian, you obviously you're going to want to track, like, here are the things that I have sent that are on the disks. Here are the things that are in flight right now. Here's the files I've ingested. So, you can tell what's different between you and some other instance of the Librarian that's running. And then, so you can use, in addition to kind of just a database that's running that you're sending queries to, you can use an object relational mapping, like SQL Alchemy is the one that we use. And what this allows you to do is take your Python objects, stuff them in the database, and get them back. So really this kind of combination of I can respond to requests and I can store stuff in a database and retrieve it is classic web programming, right? But it's something that scientists are a little bit afraid of, and I don't fully understand why. So what does an ORM class look like? It's just like a regular Python class, but with some additional annotations that tell you what the database types of the things in the database are. So here, I have a path. Let's stick it in the database as a string. I have the name of the file, also a string. I have an ID, that's just an integer, these kind of things. So in addition to this kind of classical, request response model, in a data management tool, you need to have some idea of kind of running a task without any input. Things that go through and check the integrity of files, things that make copies of the files on their own. For instance, one background task that we want to do is say, hey, did you receive anything new in the past week? You should put it on one of those Sneakernet drives so someone can carry it to North America. Because if we don't do that, then we're going to spend all of our time sitting and waiting for the data to be copied when we could have been copying it as it came in. We do this through Schedule, which is an extremely lightweight Python scheduling library. Schedule's great. You can think of it as cron in Python. And we use it on the web server to do all kinds of stuff. So it runs in a separate thread, but it has access to the same database. This allows it to go through and make very easy queries to the database and send stuff to other librarians, for instance. And then I think the final piece of building something like this is a way to configure it. And Pydantic settings is really the way that I would recommend configuring any project in the future. So what this allows you to do is write a Python class that is a Pydantic model that can be loaded from a structured file like JSON or YAML, of course, but you can also automatically overwrite any of the fields with environment variables. So things like your database password file, the name of your server. These are much easier to configure using environment variables than they are with actually changing the files. So with all of these pieces put together, a web server, a way of tracking the metadata persistently, a background task scheduler, and some way to put the right strings in the right places, we have the Librarian service. So how do we get data into the Librarian? This is the only touch point that anyone who is using the Librarian who isn't an administrator will do. You push stuff into the system and it makes it appear in the rest of the world. So we wanted to make this as easy as possible. So there is just a single function, that's upload. You take your local file and you say, I would like to place it in this position in that kind of global namespace. And what this does is take your file, upload it, and you're done. How does this actually work, though? So let's do the easy case, which is Globus. So let's say I have some experiment data, and I want to upload it to the Librarian instance that's running like co-located with the telescope. The worker that is kind of at the end of the data packaging step says to the server, I would like to upload a file. Here's how big it is. Here's its checksum, and so on. Our librarian then responds with a specific path to place that file in. One of the notable things that we found that simplified this whole process is delegating as much stuff to other programs as possible, kind of obviously. So permissions checking, all of that is handled by the Unix file system and not by our system in a whole separate case. So you place the file where it needs to go, and you tell the librarian that you're done. It moves it into that kind of reserved space that I showed at the beginning, that kind of file system set of paths. And then the background tasks come along, pick it up, and effectively upload it to a second librarian. And the data is shipped using Globus. In the Sneakernet scenario, things are a little bit more complicated. The upload happens in the exact same way. You upload your file to the local librarian, but after a while, that drive's going to fill up. And this is one of the things that most data management tools don't really have a way of doing, is saying, hey, the drive's full. Someone's got to come along and unplug it. And so we send Slack alerts, and the people who are on site they pick up the drive. As part of that process, we generate a manifest that tells you everything that is on this drive, its checksums and so on, where it came from. You fly it to North America, and we have a manifest ingestion process on the other end that includes some callbacks to the main librarian over the internet. If those callbacks fail, like if our telescope is completely cut off from the internet, this still works. There'll just be some dangling things in the database that will need to be cleared up. And we have some hypervisor tasks that go through and make sure of that. So this is the librarian. I think I want to end with some kind of lessons that we learned whilst we were building this, that hopefully you can apply to some web services that you'd like to build. We found dependency injection incredibly helpful. So dependency injection is a programming technique where you specify the dependent services that your program needs to use in a homogeneous way. So when we say, I would like to transfer a file from path A to path B, we always use this function here, transfer. And this abstract base class is filled out with very different code depending on the service that's being used. For Globus, there's a whole separate thing in here than if you just use the local file system copy, for instance. And this really also helps with testing, because Globus is horrible to test with, because you have to have like sites that have subscriptions and all these kind of things. Another lesson that we learned is that having a service layer in your web application is very helpful. So if you think about making a request to a service like this, you get some data that comes in, you transform that data a little bit to prepare it for an interaction with some service like the database or the file system. Then you have to handle errors, like what if someone uploads a 1 billion terabyte file? Well, your file system isn't going to take it. And then you create a response object. The trouble with this is that, one, it doesn't pair as nicely with dependency injection as you'd like, and two, you can't obviously reuse these layers elsewhere, and three, it makes your routing functions incredibly complex, and that's very difficult to debug and refactor. So if you package this central bit up into a service layer in a similar way to the dependencies we just talked about, it's much easier to reuse this code elsewhere. And this is, your classic don't repeat yourself kind of stuff, but specifically applied to these external services that you're dependent on. Testing applications like this is really hard. If you go to a restaurant, you can ask your waiter anything. It doesn't mean it's going to be helpful. You can say to your waiter, I would like you to pick up my dry cleaning. They're going to tell you no. You can do the same thing with a web server. You can ask it anything. And so you need to test for all these kind of scenarios. Integration testing hence can only really get you unit testing can only get you so far. You're much better off trying to do integration tests and end-to-end tests. And as I said before, if you're writing something that's dependent on the Globus API, make sure to prepare for that early, because Globus is really hard to test with. Something that we found that is just revolutionized our way of testing this application is pytest X process. This allows you to spin up an entire copy of your server as a pytest fixture. So your whole web service exists in a separate process, and you can interact with it. And so you can spin up a dummy thing, fill it with fake data, interact with it, crash it, do whatever you want, and then pytest just magically makes it go away. And this, alongside test containers, or if you can use your database with SQLite instead of Postgres as a swap out, this makes testing much, much easier. So that's kind of it from me. The Librarian, as we've introduced it here, is our simple kind of open source data orchestration framework. It's very useful in these environments where you may have to move data by hand. If that's you, very happy to talk with you about how Librarian can be applied to your scenario. I think that's less likely here. It's a very odd scenario now that the internet is everywhere. 20 years ago, it may have been a different story. But I think the thing to try and take away from this talk is that by taking these kind of very simple components, you can develop a solution designed for your exact needs. And you should give web frameworks a go for your scientific tasks. It's much easier than you think it is. And your web applications don't need to be these kind of polished, perfect things with a wonderful UI. The Librarian has no UI. All of our kind of, what's going on introspection happens through Grafana, which is a whole separate service. We didn't build a UI for this project because it didn't need one. And don't think that, if I'm making a web thing, it has to have a million things attached to it. It can just be a simple product that does a simple job that you can host somewhere. And that's that. Thank you, everyone.
That was a great talk, so thanks very much. Okay, so we have about 5 minutes for questions before we have to go to the passing period. So are there, there's a few questions that were on Slack, but are there any in the room questions? Yeah, we have one here.
Hey, thank you for the talk. I'm Tudor, work with ORNL. We have a similar system, and I was curious, the manifest, if you go to the diagram you have where you showed the second one, this one.
Yep.
So the manifest, how does it get to the destination? Is it with the disk or?
So we place the manifest on the disk and also send it over a limited network bandwidth. So in this scenario, we usually have that radio link. That's super reliable, but we need it for actually accessing the computers at the site. So we can send the manifest, that's just a JSON, to make sure it gets there, because the last thing you want to do is lose the drive and the record of everything that is on it. That's not good. So we make multiple copies of that and send one kind of ahead of time to the destination. If you have a similar problem, you know that it is inherently a manual process, right? Like, anytime you have to tell somebody, can you go into that room and unplug that disk, and you have to tell them to do it twice a week, there is a little bit of manual work involved, right?
Yeah, I can relate.
Yes.
Thank you. And one more question, if I may. The Librarian GitHub repo, is it under NERSC?
No, it's under the Simons Observatory GitHub. So if you go to Simons Obs/Librarian, it's there.
Thank you.
And then it's based on a kind of, I would say it's based.
Can you pull that up live right now so people can see it on screen?
Sure. There's not, it's not the best repo in the world. As I said, it's a very simple tool. Let me just. Simons Obs. So yeah, this is based on a older tool that was made for Hera, which was a previous observatory, but we rewrote the whole thing. I don't know if you can actually see my web browser here.
No, sorry. my suggestion was bad because, oh, no, now we can. Now we
There you
can,
go.
great.
Yeah, so it is officially a fork of that, but it's an entire rewrite that happens to be in the same repository that we haven't figured out yet.
Okay,
So we're
nice.
400 commits ahead.
Okay, and then we had another question on Slack from Oleg. Is Oleg here in the room? Yeah, there we go.
Hello.
Hi.
I was curious, since you have to take these hard drives and transport them manually, has there ever been an instance where a hard drive got damaged or?
Thankfully, no. We do have the facility to say, hey, here's all of the things that we lost, though I've never had to use that. Thankfully, so far, the fiber has been operating, and we haven't had to kind of pull this out again. This was something that we had to use early on in the stages of the process. But as I said, there is one fiber that goes up the hill, and so if someone comes along with a digger, we have to very rapidly switch to this. Yeah, but we have facilities to do that. I mean, the manifest contains a list of all of the files, and so if you just basically go through and copy them to a fresh disk and send them. But thankfully, we use Peli cases, and we use these kind of more rugged drives, like they're designed to be not bashed around, but maybe a little. And so we're kind of okay so far.
Thank you.
Okay, we're doing good on time. So we also have a question from Kevin. Is Kevin in the room or?
Yeah, I was just curious, like for your Sneakernet implementation, do you see like the new relatively low-cost, high-bandwidth services like Starlink or Amazon's upcoming competitor?
Yeah, I mean,
changing how you do
satellite
things?
internet is still way too expensive for us. It is an additional cost that the project can't necessarily take on, and it is still a petabyte a year. Getting that over Starlink isn't cheap. And we have to send people up and down the mountain anyway. Like, sure, it would be great if we had a Starlink thing, but one, astronomers don't like Starlink for many reasons. But two, it's just an extra expense that we can't afford to bear, basically. Yeah.
Okay, I think we have time for one minute question. So, do it. All right, we got one over here.
Hi, I'm Kari Barry. I work for the National Synchrotron Light Source too, which is a synchrotron, and we work on a data access platform that's somewhat similar. It serves FastAPI. It's called Tiled, and basically restifies data and adds authentication and security. I was just wondering, sort of, when you started to work on this project, it looks like it's mostly made from the bottom up, from scratch. Did you look at other extant projects that do similar things like SciCat at Berkeley, or what made you decide to go with this ground-up approach other than just you have this bespoke data separation problem from the physical hard drives?
Yeah, I mean, there is this bespoke problem. We did look at a bunch of the data management tools. We didn't find one that we could kind of easily adapt to behave in this way and also give us this kind of control over the different sites that was completely disconnected. So a lot of these distributed systems, and I don't know if the one that you're talking about off the top of my head, but they kind of are linked together. The Librarian, by its nature, is an incredibly distributed system. Like, the person who manages that instance manages all of the data there, and all that happens is that they get sent stuff that's new. And so the different system administrators at different places, they all want to manage their data very differently. And so this was another reason that we built this, is that we can completely decouple like what happens at site A and site B, and all we do is make sure that they get sent the data, and then it's up to them to put it where they want and transform it and all of these kind of things. So yeah, I mean, of course, there's always scope creep in these kind of projects. You start out thinking it will be a simple thing, and then maybe it's not as simple as you thought. And that maybe contributed a little bit as well.
This definitely got the wheels turning in terms of what would a PR look like to add that sort of feature to tiled or any of these other frameworks. That distributed nature is really interesting. Thank you.
Thanks.
All right, I think we're at time, so let's thank Josh again for the great talk.